All right, welcome back, guys. This will be the second lesson for chapter 2. The title is Functions. We are going to start discussing things a little more formal in sense of the concept of mathematics. Ones involve certain equations and how do we graph it and how do we classify those equations. So the title is called Functions. So let's start with the definition of function. So it says that a function is a special kind of a correspondence between two sets. Um, so what that really is saying that we have two sets. We can say set A and set B, right? A correspondence is like a relation. So we say a relation, right? So something that describe one thing relate to another, and it's a special kind of relationship here. Relation, sorry. Um, and let's look at this example. We have for each person in a class, there corresponds a day of birth. Okay, so for every person, for each person, can only has one date of birth. Um, and for each barcode in a store corresponds to a single price, right? So you pick up two items, or pick up a single items, anything randomly in the store, and you scan the barcode. Well, when you scan the barcode, the computer will tell the price for that item, not two price, just a single price, right? The example is that for each real number, there corresponds to the cube of that number. Meaning, let's say we have 3 as a real number, and then that one corresponds to the cube of that, which is 27, right? So there's no two possible cube for 3, right? The first set for the relation or the correspondence, we call that the domain. So the domain is the set of all inputs, and then we run that through the function, and we get the outputs, and the outputs can be called the set of the range. Furthermore, it says that for any member in domain, there is exactly one member in the range for which it corresponds to. This kind of correspondence is a function. So to summarize this up, we say that a function is, you can say a function is a relation or correspondence such that for each input, we're going to call input as x value. That's what we're more familiar with. Relates or map, in other words, maps to exactly one output. And the output, we can call that y value. Okay. So we have x value mapped to the y value. A single input must map to exactly one output. Okay, so that's pretty much what the definition means. So let's look at this in a more straightforward example, or more of a really, not easy, but it's more like a concrete or finite example. Okay, so let's look at a math example. Okay, so let's say we had an example. So let's say we have this relation. Okay, given this relation, let's call this relation S. Okay, and then this S is a set of all this ordered pair. We'll say we have 1, 2, comma, 2, 5, comma, 3, -4, comma, -1, 7, right? So this set here is a relation and describe what's going on with this x and this y value. So we can say here's all the x, here's all the y. So let's say we have x would be 1, 2, 3, -1. The y would be 2, 5, -4, 7. Okay, so it's saying that, hey, the first order pair, let's take this 1 and map that to 2. And then the second order pair, let's take this 2 and map that to 5. And then 3 goes to -4. and then -1 go to 7. So notice that each input has exactly one output. Okay, so we say that this set here is the domain. Okay, so the domain will be the collection of all these inputs. So 1, 2, 3, -1. And then this will be the output, which is called the range. So it's just a collection of all the outputs in that function. Okay. So think of function as like a machine or a formula. So we can look at this as, okay. What we can relate to is function is like a formula, right? Formula, we know in real life, we plug in something in formula, we get the answer, right? What would be example that's not a functions? So not a function example. Okay, so let's say we can look this as a diagram. So we can say, okay, 1 get mapped to 2, 5 get mapped to 7, and then 5 also get mapped to 10, right? So in this case here, this is a non-function example. Why? Because we have an input of 5 get mapped to 7 and 10. So in this case, 5, 7, 5, and 10. So it violates the definition of function. Why? Because this input phi here does not have exactly one member in the range, right? So input phi does not, actually not, we can say if it has more than one output. So that's what make this fail. So we can say, so this relation is not a function. Okay, so in the homework there will be a couple examples where they ask you to identify certain correspondence is a relation or not. Excuse me, certain correspondence or relations is a functions or not. Okay. So the part where it gets a little more confusing is when we go from a finitely many ordered pairs relations or correspondence to an infinite many ordered pairs, and then identify whether it's a functions or not function. Okay, I'll give you an example. All right, so let's say we have an example of this here. So we have the equation, say equation y equal to, let's use the previous one, y equal to 2x minus 1. Okay, so let's say, this equation here, let's say we have x is 1. Well, when x is 1, we're going to get 1 for y. Okay, and when x is 0, we're going to get -1 for y. And when x is 0.5, well, 2 times 0.5 is going to be 1. It's going to be 0. It's going to be 0 for y. Well, can we list all the ordered pairs for this equation? Well, it turns out there's going to be infinitely many ordered pairs for this relation or correspondence. So in other words, this equation here describe how x relates to y. So we can just list a few here, and there's a lot more. Okay, so when we deal with equation that has unknown variable x and y like this here, chances are that equation has infinite many ordered pairs. How are we going to go and collect all the domain and range like this? Okay, so it becomes a little more difficult to do that. Well, one way to figure out the domain and range for this is we can graph it. Okay, so from the previous lesson, I'm going to go ahead and just copy that from my previous lesson here. Oh, there it is. So I'm going to go ahead and copy and paste. So I'm going to go ahead and copy this. Copy. Okay, so and I'm going to paste this here. So from the previous lesson, we got a graph of 2x minus 1. Okay, so if this is the graph, okay, and it describes all the possible ordered pairs, well, what would be the set of all inputs? Meaning, what is the domain? Okay, in other words, can we find out what are all the possible values of x that we can plug into this equation? If this is the graph, if this is graph how it looks like, this saying that it's going to extend this way indefinitely and this way indefinitely. So can we really figure out all the possible value of x? The answer is yes. Well, let's ask this question. Is there a value of x that can't be used in this equation? The answer is no. So, if I pick any x on the horizontal axis, okay, any possible x at all, well, any of those x I pick will correspond to a y, right? Whether it's decimal or fractions or whole number. So the domain in this case, the domain is all x values. Okay, you can write this as interval notation. You can say from negative infinity to positive infinity, or you can use the set BO notation. You can say domain is x, where x is any real number. Okay. In other words, the domain is the entire x-axis here. And it's going to be the same thing for the range as well, right? So there's no restriction there. So the range is going to be r equal to, we can say, y, where y is a real number. Any real number. Okay. So that's where things get a little more complicated, is when we go from a few ordered pair where it consists of few inputs and output to an indefinite or an infinitely many ordered pairs where we can't really list out all the possible inputs and outputs anymore. We kind of have to rely on our intuitions and our visuals to understand what what will be the possible inputs and outputs will be. Let's look at another example. Perhaps it's become more clear if we look at a more example here. So let's say we look at an example. So given the graph, okay, let's find the domain and range. Okay, so let's go ahead and do that. I'm gonna go ahead and copy a graph from this previous one real quick. I'm gonna go, not crop. Let's go back. Actually, I'm gonna do this. All right, so copy. All right, so let's paste this here. All right, so let's say the graph looks like this. Here, let me draw the graph here. Let's say we have a graph that looks like this. Oh, not that way. So that's the graph, okay? Well, notice that this graph starts at 1 for x, and then, it goes to the right. So let's say I pick here's for x, or here's for x, for example. That's going to be my y. And here, if I pick this for x, it's going to be y right there. So any x value on the right side of 1 is going to be, eligible for the input there. Okay, so in this case, the domain, we can say the domain, okay, so the domain is everything past 1, including the 1. So we can say domain is all the x such that x is greater than or equal to 1. Okay, and the range is the output. Right, here's x is y. The range is going to be everything, coming out from the graph, or the graph itself. So if you look at the graph, okay, it's going to do this. Well, the range is going to be all the output, which is all the y values. So the lowest y value is at 0. It's going to be all the way up to positive infinity, right? So let's say if I pick here from here's my x, the y is gonna be over here somewhere, right? And then this arrow will indicate that it's gonna keep going like that, right? So the range in this case is all the possible output y, such that y is greater than or equal to 0. Okay. All right. Another thing that comes up is without an actual list out mapping like like this here to know whether each input has exactly one output y, how can we tell from the graph whether this graph here is a function itself or is a correspondence that considers to be a function? So how do we do that? So let me go ahead and erase this again, and I want to redraw the graph. Okay, so let's say if this is the graph again, okay, how can we determine this graph is a function? So there's this thing called vertical line test. So vertical line test. So we can draw any arbitrary vertical line through this graph. So let's say I'm going to draw a random vertical line like that. Okay. So notice that if I draw this vertical line test, there's only one intersection point there, right? So notice that, the vertical line intersects the graph only once. Okay. What does that mean? It means that at this point there, this input x corresponds to one single output y. So that means each x relates or corresponds to exactly one output y. Okay. So in this case here, this graph here is a function. Okay. Now let me give you an example where a graph is not a function. Okay. So let's say we have a graph like this. Let's say we have a graph like this. Maybe perhaps sideways like this. Sure, like that. Okay. So let's say if this is the graph, let's draw a arbitrary vertical line through this. Let's say this is my arbitrary vertical line, right? So this one, the vertical line, intersect the graph twice, right? Okay. So what does that mean? It means that at this point there, that point there. All right. So let's say here's our x. So this x here map to two different y value. So let's say that's y1 and this is y2. So in this case here, this x here map to y1 map to y2. So this violates the definition of functions. So the definition say that for each x must correspond to exactly one y or one output. Right, so the vertical line test kind of a cheat way or quick shortcut way to determine given graph. Is a graph will constitute a function? Right, you draw vertical line test through the graph. It intersect more than once, then it's not a function. If it intersect exactly one time, it is a function. So this is a quick way to determine if a graph is a function or not. Now notice that this doesn't really tell us. This doesn't really help us determine the domain, the range. That takes a little more work with a lot of example practice there. The last thing we're going to talk about in this video is function notation. I probably would want to save this. Yeah, I'm going to save this in the next video because I don't want to create an hour video long here. So I'm going to pause here in the next video of this lesson. I'm going to do several more examples related to this lesson.